Okay, Pathways class. Let's see here. Yesterday I gave you, for those of you, about 15 of you, which was good. Looked at the earthquake and seismic wave and P waves and S waves material. And you were right on point. I looked at all the documents you handed in and you answered the questions well. What we're looking at here is we want to try to look at the Earth structure and how we know, or what we think we have a really good idea of what the Earth's interior looks like based on earthquakes. All right. So what we have here, first of all, is this model. This is the Earth right here, cut in half. This thin section here is the crust. This is where we live. Okay. And this is the crust, very, very thin. The thickest layer here, all right, let me just label this crust. We'll type because you know my handwriting. This is the crust. All right. That's that outer layer right here. That's the crust. All right. Here, if you remember from long ago, this is the mantle. That's the thickest layer. That's like the liquidy lava-like. It's called magma when it's inside the Earth. It's magma, melted rock. It's sort of oozy, gushy, not quite solid, not quite a liquid. Some of it more liquidy than others, and some more solid than others. Then here, we'll see if we can drop this, make it smaller. This is the inner core. Inner core here. I can't make that quite small enough. We're just going to put it right above it. That's the inner core. And this would be the outer core. All right, what do we think we know about these? This inner core, we believe, is solid, and it's made of a mostly iron, and it's actually spinning, if we can get that in there. Yes. So the inner core is iron. We believe this outer core is liquid, and then this is sort of a solid liquidy material. So how do we know that? So one way we know this, or we think we know, is through earthquakes. So here is point, we're going to call this 1, and that is a seismograph, an earthquake detector. And we're going to make this 2. Okay? And we have P waves and S waves. P waves and S waves. The P waves can go through anything. Okay, they can go through solid, they can go through liquid, they can go through gas. That's a seismic wave. The P wave, the P is actually for seismic wave. That's more like the longitudinal wave. It can go through anything. Okay, so P waves can go through anything. Through anything. And S waves can only go through a solid. Through solids. Okay, so how does that help us? If an earthquake happens here, it's going to send out both P waves and S waves. Okay? And what seismic monitor number 2 is only going to get, so I'm going to put the P waves in purple. The P waves can go through anything. So the P waves are going to go through anything. So you're going to get P waves here. You're going to get P waves here. You're going to get P waves going through. Now the S waves, we're going to put in brown. They can only go through solids. Okay? So as the S waves come down, if it's here, it's going to go through. Okay? S waves can only go through solids, so I should have drawn it. All right. solidy, liquidy. It's going to go through, but it's not going to go through this outer core, which is liquid. So we're not going to get any S waves going through there. So right here, there's going to be this void where we're not getting S waves. So we think there's something liquidy in the center because these S waves, it would go this way, and we'd pick it up at a seismic monitor over here. Okay, we can get S waves going through the rock. Remember that magma is sort of rocky. We're going to get S waves, but we're not going to get any S waves on any of these monitors here, which means blocking there must be some liquid, because there's earthquake monitors all over the earth, and it'll get S waves from all over here, but it won't get any S waves where this liquid is. So there must be some liquid here blocking the S waves from going through, because S waves are going to show up all over. Those S waves will show up, but they won't show up in the shadow, if you will, of this liquid. No S waves are here. Now the P waves, they go through anything, and they also change speed as they go through different material. Just like a sound wave, when it goes through water or steel or air, it goes through at different speeds. So as these P waves go through, they're going to change speed when it hits the liquid. They're going to change speed as they hit that solid, and they're going to change speed when they hit the liquid, and they're going to change speed again here. So we can notice how a P wave changes speed here, but doesn't change speed over there. So if it's going through the magma the whole time, it doesn't really change any speed. It doesn't really change speed here. It doesn't really change speed there. But what a P wave will do is it'll change speed as it hits this liquid, and then change speed again. That way we can get an idea of how big that outer core is, because we can look at the speed change in those P waves. It must be from here to here. How long did it change speed, and when did it change speed again? So that's a couple of ways you can tell what the inside of the Earth looks like. You can also tell that through on other planets. If we were to get to another planet, we can, if there's movement in it, or if we caused a movement, if we caused some sort of small quake on it, a motion, and then had detectors, we can get an idea of what their inner core, outer core, if there is one, what it looks like based on the seismic waves. Okay. If you want to learn more about waves, P waves and S waves, and tell the difference, I'm going to put a link in the YouTube channel about determining what the inside of our planet looks like based on the P waves and the S waves. Okay. All right, that's it for today. I hope everyone's doing well, and I'll see you tomorrow.